All right, here we are, section 12.5, the normal curve. This is probably about where statistics gets kind of like with the standard deviation calculation. It's a little difficult, but keep in mind, I would not expect, and I think most in math instructors would not expect you to remember every single step of the process that will be outlined in this section. If you can write all the steps down on a 3x5 note card and understand what you wrote and then do it, then that's fine. I don't feel like you need to expect yourself to remember everything in here. Just if it's in front of you, know what it means and know how to do it. That's all. Um, this is probably the most important thing in statistics. Arguably, that it's everything's been kind of building up to this so far in this chapter. But here, just so we can kind of encompass everything, the last section, 12.4, was pretty short. It wasn't much, but it was leading to this. This section will be pretty dense, maybe. These are the things that we are going to learn in this section. We're going to be able to understand properties of a normal distribution, and we'll talk about what that means. What is a normal distribution? You've probably heard about it before. Also, we need to calculate what's called a z-score, which we'll see what that is, and we'll use it to determine the area under a normal curve. And we'll see kind of what those have to do with everything. But we'll use this to calculate probabilities. Yeah. Probabilities. It's like, just imagine if you had a big set of data values of, let's say I was interested in what's the average height of a man in the United States or something. I'd probably ask a bunch of men, how tall are you? And they'd tell me their heights. And then I'd get this distribution. I'd probably calculate the mean. There's the average. And then the standard deviation, like we saw in the previous section, which kind of measures how far from the mean or how far from the average most data values are. It's kind of like an average of the average. The average distance that each data value is from the mean. And then once I have all those data sets, I could maybe come up with some ideas by like how I can figure out the probability that some random man will be shorter than, let's say, 5'5" or something. What's the probability based on all the data values I had before? I can calculate that, or based on all the data values that I've gathered, what's the probability that a man will be taller than 6 feet tall if I just pick a man at random in the United States, something like that. That's the kind of probabilities we're talking about here. But also we're going to figure out how to calculate the percentage of data between any two data values in a normal distribution. So that's, yeah, not just like I was alluding to, what's the probability that someone's shorter than this or taller than this, but also between this height and this height. What's the probability that a random man in the United States will be between 5'8" and 6'1" or something like that? Then I can calculate that probability based on data values I've gathered and calculations for mean and standard deviation and stuff. So kind of interesting, actually. Now we're using data to make predictions about future values we might come across. But before we get into all that, let's talk about what is a normal distribution and what other kind of distributions are there. This one you don't see very often, but it is a thing. It's possible. A rectangular distribution is when all the observed values occur with the same frequency. So that doesn't happen very often, but I guess if your data values were like, let's see, for example, if you had, I don't know what I'm measuring here, like how many hours of television you watch. I always go back to that same one. So like 3 people said 2 hours, and then 3 people said 7 hours, and 3 people said 11 hours or something like that. And actually, I'd have to have all the values in between. 3 people said 2 hours, 3 people said 3 hours, 3 people said 4 hours. You know, that's kind of ridiculous. What are the chances this happens? 3 people said 5 hours, 3 people said 6 hours, 3 people said 7, 3 people said 8. That's hard to imagine. 3 people said 9. 3 people said 10, and 3 people said 11. I mean, of all those data values, of course, if I do like a frequency distribution like we've seen before, I would have, here's how many times that happens. Here's the number, 2 hours of television, 3, 4, etc. They're all going to be the same height because there were 3 data values of each, right? I mean, I saw 3 people say 2 hours. I saw 3 people say 3 hours. 3 people said 4 hours. You know, etc. That doesn't happen very often, but that's what we would call a rectangular distribution, only for the fact that when you create a frequency distribution, it ends up looking like a rectangle. Someone was not very creative when they came up with that name. But that's a type of distribution, doesn't happen too often. You can also have a J-shaped distribution. That means the frequency is either constantly increasing or constantly decreasing. So there's always, so either the smallest number it happens less than the next smallest number, it happens less than the next. It has to be constantly increasing, or the opposite. Maybe let's see, like, for example, if it was just the hours of television, here would be like, oops, the left graph would have to be represented with maybe one person said they watched 2 hours of television, maybe two people said they watched 3 hours. It doesn't have to be increasing constantly like that. It could be maybe now 5 people said 4 hours, and then like, I don't know, 6 people said 5 hours, maybe 7 people said 5 hours, just to be silly. Something like that. Then I would say for that, my frequency distribution, there's only one person that said they watched 2 hours. 2 people said they watched 3 hours. And how many said they watched 4? 5 people. 3, 4, 5 said they watched 4 hours. And then how many? 7 said they watched 5 hours. I made this up and I already forgot. Yeah, there we go. So that would be a J-shaped distribution, because it kind of looks like a J if you squint at it hard enough. I guess like that. That looks like a J. This is a backwards J-ish. Sort of, not really. Yeah. And then this would be similar, except if I had a lot of people saying a small number, if I had maybe 6 people saying 2 hours of television, maybe 4 people saying they watched 3 hours of television, maybe 3 people saying they watched 4 hours, 2 people saying they watched 5 hours, something like that. Then I'd have, yeah, that's pretty much it. But the chances of that happening randomly when you gather data aren't too great, but it could happen. And this one happens a lot with when we grade midterms. A lot of times in math classes, or any classes probably, you have a lot of like B's maybe. So these are, let's say these are grades F, D, C, B, and A. Usually there aren't too many A's. There are a lot of B's, maybe some C's, a lot of D's, and then not that many F's. That's what we would call bimodal, because there are 2 grades that stand out a lot, B and D, for example. There's 2, yeah. So anyway, it's by definition, 2 non-adjacent values occur more frequently than any other values in a set of data. It happens a lot with grading, especially when you have ranges like this. F is from 0 to 50%, D is from 50 to 60%, and oh no, F is from 0 to 59%. Anyway, sometimes that happens, but probably more often than the J in the rectangular distribution. This happens quite a bit. Maybe we'll see some examples of this coming up. Skewed distributions. It has more of a tail on one side than the other. It kind of looks like a J distribution. I guess if, let's say I only focus on part of it, I'm going to erase this after I'm done, but like, let's say, oops, I only focus on here. I'm just trying to, this, if there was just this and there was nothing over on the left side, that would be a J distribution, because it just constantly decreases as I go from the beginning, the very topmost part, all the way down. And then similarly here, if I were to cut off the very right side, I just look at this, that's a J distribution, like we saw earlier. But J distributions only apply when the very left or the very right is the highest peak, and then it constantly goes down from there, constantly goes up from there, whatever the case may be. But here there's a peak, but it's not on the very left side, it's not on the very right side. It's somewhere close to the left side or close to the right side, but not exactly on the far side. Anyway, they call that the skewed distribution. It's like the highest value is either skewed one way or skewed the other way. And for me, I don't know why, but the difference between them, this one is skewed to the right, this one is skewed to the left. I always want to say the opposite. I feel like the one on the left here, there's more data values on the left. Like here, most data values are on the left. Data is on the left. You can tell because the peak's higher on the left. So I want to say that it's skewed to the left, but no, you actually say it's skewed to the right. So what, I don't know if this helps anybody. This helps me when I imagine someone sliding down here. They're sitting here, they're saying, wee. If someone was on here, which way would they slide? If they were sitting at the top, they would slide down this way. So they're sliding or skewed to the right. I don't know why that helps me. And then same thing here, even though most of the data values are on the left, or sorry, I got them mixed up. Most data values are on the right because the frequency distribution has the tallest peaks on the right. But if there was a person sitting there, he or she would start sliding to the left. Yeah. Why do I get my left and right mixed up? That's not good. So wee. You could throw that in there if you want. All right. Sometimes math gets boring. You gotta make it fun while you can. And this guy's definitely smiling. He's having a good old time. Okay, that helps me for some reason. I always want to, yeah, say it the other way. Skewed to the left, skewed to the right. All right, and if we just smooth that out, like if you go back to the frequency distribution and you kind of like connect the peaks and just want to make a curve out of it, sort of. It looks kind of like this. That's how kind of the curve would look for skewed to the right. And if I do something similar on the skewed to the left, it would look like. There we go. I guess imagine if the thickness of each of these categories was skinnier and skinnier, got narrower and narrower, then it would end up looking like this curve eventually. Skewed distribution, smoothing the histograms of the skewed distributions to just curves instead. So imagine there's a frequency distribution underneath here, but this is the basic shape of it. If you just imagine those, yeah, each of the categories gets narrower and narrower. Let's see. So this is the interesting thing about skewed distributions is there's a certain relationship between the mean, the median, and the mode for curves that are either skewed to the right or skewed to the left. So notice that the mean, if I'm going to focus on the ones that are skewed to the right, those are the ones that have the majority of your data values are on the left side. The mean, I guess, the mean, he kind of gets skewed by the smaller values. Like here, there are probably a few tiny values, but most of them are in this area. The mean kind of takes into account even the tiny values, and he gets kind of pulled towards those ones. Actually, that would be large values. Sorry, large. Because I'm thinking of this is like the x-axis. On the right is the large values, right? I think an example I saw of this in a different book is like, let's say salaries of some people at one company, of employees at some company. At a company, you got mostly people that are just like 9 to 5 people working. Let's say they got 55 grand. There's one salary, and then you got, I don't know, 68,000 is another salary, and then you got maybe someone's making pretty good money here, 87,000. I'm just gonna try to make up just a few, and then maybe someone's making 90, blah blah blah, and then all of a sudden here's another guy or girl making $1 million a year, and these are nice round numbers. But in that case, that's kind of something, if you were to draw a frequency distribution, you'd probably see, and of course I'd probably try to have more data values than that. But that's kind of the idea, that these values are kind of close together, 55,000, 68,000, 87, 90, but $1 million's way the hell out there. So that's how this curve would look. You'd see some smaller data values. They're not small, but compared to that 1 million, of course they are. Then you got your one guy over here making 1 million. And then of course the mean, if I were to average all these guys, find the mean, it would be something larger than 90,000, because the mean gets pulled towards that large value. If I add them all together, maybe we'll just do it just for fun. If you don't give a rip, then you can fast forward this if you want, or go faster. Just to show it. If I were to average these out, okay, 55,000, 68,000, 87,000, 90,000, and 1 million, the mean, he would be definitely skewed towards that larger value. So and then I'm going to divide by 5, of course, because there are 5 values there. Okay, what do we got? 55,000, 68,000, 87,000, 90,000. And then I've got 100,000. It looks like 400,000 over 5. Oh, sorry, 300,000 over 5. What the heck? Which is 60,000. Wait, that can't be right. What did I do wrong? Hold on. Sorry about that. Sorry, I can't. My big fingers pressed the wrong buttons on the calculator. It should be 1,300, or sorry, 1,300,000 divided by 5. That'd be 260,000. So the mean of those salaries up there is 260,000. But if you look at those salaries, this mean isn't even close to any of those, except it's kind of close to this guy. But that's not really a good reflection of the average person's salary in that company, right? If you saw that, someone said, "Oh, you want to come work for us? Look, the average person here the mean makes 260,000." Yeah, but that's because the mean gets pulled towards these super big or super small values, and really the average person is probably going to make more like one of these. So yeah, sometimes the mean isn't a good measure of central tendency, as we saw in a previous section. The median might be better, right? Remember the median, that's just look like the guy in the middle. This guy, that's maybe a good measure, right? It's like, that's kind of average. 87,000 is right in the middle of all of them. And then the mode, that's the one that occurs most often. So since these curves represent a frequency distribution, the mode is just right at the tallest peak. The mode is the one that occurs most often. Remember, mode is the tallest peak. I don't know if that's not a technical term, but you know what I mean, like in a mountain, because it occurs the most often. And then of course, in a frequency distribution, the height of where you are on the curve is how often it happens. So you're at the top because that's the one that's happening the most. Yeah, so probably in a situation like this, the skew to the right, skew to the left, the median or the mode, probably the median is probably your better measure of central tendency. Because if I saw that the mean income, or not income, salary of someone at this company was 260,000, I might be very excited. And then when I find out it's not that much, I'd say, hey, what the heck are you trying to, I mean, the median's still a good salary, but geez, compared to what I thought it was, you know what I mean? Anyway. So those are some different kinds of distributions, but the one we'll focus on in this section mostly is a normal distribution. The most important distribution is the normal or Gaussian distribution. This one happens quite a bit, and this is the one we can kind of study and make kind of future predictions about. If I take, like I said, heights of men across the US, you probably imagine it's going to look normal because there are some people that are going to be a little shorter, some people are going to be a little taller, but probably your average person is right here. And I think I looked it up before. 5'8", I think, is the average man in the US. I don't know. I think I looked that up. I might be losing my mind, or 5'9", something like that. But then of course, as you go out to high, taller or shorter, there are fewer men or fewer people that are that tall. But then let's say this is like 6'4" or something. There's not a lot of people that tall. And then even taller than that, good luck finding people that are that tall. They're in the NBA, okay? They're making lots of money. Anyway, blah, 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 blah. So that would be more like most things. And then when it's a normal frequency distribution like this, I can see this kind of bell-shaped curve, kind of ish. Then I can make predictions. If there's someone said, well, what's the probability that my kid will be born and they're going to be shorter than 5'6"? I could say, oh, well, let me use all the data that I have to predict that. But that's only because it makes a normal curve or a Gaussian distribution, as they call it. And then in the US, okay, United States. All right. Anyway, I'm going on tangents here, but these are some properties of the normal distribution. What do we got? The graph of a normal distribution is called a normal curve. Okay, that's a good name for it. I can remember that. A normal curve is bell-shaped and symmetric about the mean. So that's always a good thing. Yeah, if I look at that, the shape that I drew above, that pretty much looks like a bell, right? Imagine it's like, yeah, that kind of looks like a bell. You got this little ding dong thing hanging, whatever. Yeah. What else did they say just now? Oh my God, my memory's so bad. Don't get old. Symmetric about the mean. That's right. The mean should be right in the middle, especially if this is like a perfectly normal curve and the very middle frequency is the highest one. Yeah. Then that would be your mean right there, right in the middle. And I think if I remember right, I read that 5'8" is the average, at least in this country. I don't know about other countries. I don't know. Okay. And then what else? One more property of the normal distribution, and then we'll move on. The mean, median, and mode of a normal distribution all have the same value and all occur at the center of the distribution. Mean, median, yeah. Okay. Yeah, which kind of makes sense. Mean, like we said, if there are just as many data values on the left as on the right, then the mean would be right in the middle. The median as well, same kind of thing. The mode, well, the mode represents the highest peak, and which should be in the middle, like we mentioned on the skew to the right, skew to the left. So, okay. And now this empirical rule, this is probably something that's good to, I don't know, keep in mind, especially if you take another statistics class. These are like the benchmarks. It's good to have a picture of this. I would say if you're watching this right now and you're taking notes, I would draw the picture that I'm about to draw. Approximately, I don't know why this picture is not already in the notes. That's kind of interesting. This is from the textbook and they didn't have it in here. Approximately 68% of all the data lie within one standard deviation of the mean in both directions. Approximately, I'm going to draw a picture here pretty soon. 95% of all the data lie within 2 standard deviations of the mean in both directions. Approximately 99.7% of all the data lie within 3 standard deviations of the mean. Okay. So what are they really trying to say here? let's see. So if I drew a normal curve, let's see, here's the kind of like the x-axis. And let's say all the data values go. I'm trying to make this nice bell shape. Try to make it look symmetric. I'm doing my best here. And it's not supposed to be wavering like that, but pretend. There we go. Our mean is right here in the middle. I'm gonna I think that's like the highest peak. Pretend like that is. Okay. And then if I calculate the standard deviation like we saw in the previous section, let's say this distance here, from here to here, is the standard deviation. Standard deviation. And then I'm going to draw this, try to draw the same distance, same thing over here. This is the same from there to there. So this is sigma, the distance between the middle or the mean and this little green kind of tick mark that I've made. And same thing over here. Between here and here is 68% of all your data. 68% of all data. Like it says, lie within one standard deviation of the mean. So in this area here, if I were to draw just two vertical lines, pretend these are straight lines, and in this green area, 68% of all data is in here, in this area. And the rest remains outside. Okay, now what if I go one more standard deviation out away from the mean, like this, maybe here and here. There's another, so this from here to here is another sigma. That means how far am I from the mean? I'm 2 standard deviations away from the mean. So between here and here, like they said, is not as we say here, 95% all data lie within 2 standard deviations of the mean. 95% of all data. So if I were to draw vertical lines from those little tick marks up to the curve, and I kind of shade in that area, even the green part, so even the green part matters too, and all the extra stuff, I've got 95% of all data lie in that pink, or whatever that color is, purple, pink. And then I didn't draw this curve very nicely. I should make it more curved downward. It looks, I think I'm gonna just erase this just to make it look like it's more accurate, because the way I drew it, it doesn't look like that's 95% of my data. It should probably curve pretty harshly now like this. There we go. And then what remains is not a lot left, but if I draw one more standard deviation, let's say if I go out one more sigma away from the mean, that means in either direction I'm 3 sigmas away from the mean, right? From here to here, that's 3 sigmas, and the same thing from here to here is 3 sigmas. That encompasses, if I were to draw a vertical line up there, and maybe there's already too much color. I'm just going to highlight now. I hope that doesn't cover the purple and the green too much. But all this highlighted area, other than the little tail that is left on the left and the little tail that's left on the right, that's 99.7% of all the data. Let's see, what's another good color here? Yeah, from here to here represents 99.7% of all data values. And I know I probably didn't draw it very nicely. It looks like there's a significant amount of data in these tails, but pretend. That's kind of the idea. That's a visual. That helps me a lot, visualizing that instead of just these words over here. Yeah, about 68% of all data lie within that one standard deviation. So that part that I kind of shaded in green, just from here to here. And then 95% of the data values lie within 2 standard deviations. So here to here, and then 99.7% of them, they call that the empirical rule. And I think if you take a statistics class in the future, you might have to memorize those, but in this class, don't worry about it. Maybe write it on your note card if you want. Okay. Now what we want to do is, let's say I'm just going to draw a normal curve again, just so we kind of have it in front of us. Here's mu, and let's say here's my sigma, standard deviation here. I calculated, who knows what this is talking about? Maybe it's still heights of men or it's something else. I don't know. But what I want to do, let's say, let me erase this part. It kind of doesn't look great. I'm trying to make it look symmetric, but I'm not an artist. That's why I'm a math person, I guess. Let's see. Yeah. All right. But what I want to do is be able to take any random data value, or yeah, like let's say if we're still talking about the heights of men in the US. If someone said, what's the probability that someone can be, I don't know, let's see, someone said probability that a man in the United States is, I don't know, taller than 6'2" or something like that. I'd say, well, how does that compare to the mean? The mean is here, 5'8". And I don't know the standard deviation, but I think 6'2" would probably be somewhere over here, maybe. I don't know. I'm just guessing. So what is the probability of me having the next person be here or more taller? That'd be somewhere over here. I have to figure out, I have to find the area beneath the curve over there. That's what the probability is, the area under the curve. And that, we just have to take that on faith because that has to do with calculus. If you take calculus, you'll learn probabilities and area under a curve are related to each other. And then actually, in order to find the area under the curve, we'd have to use calculus. But in this class, we just have a table of values. We're not going to do any calculus. Don't worry about that. But it's kind of interesting to know that everything connects: statistics, calculus, probability, all that stuff. That's what we want to do. So we're going to end up having to do something where we compare, like this guy. If I want to know what is the probability of being 6'2" or taller, that actual number, what does it depend on? It depends how far away from the mean it is. You know, how far away is 5'8" from 6'2"? Of course, the closer they are, the probability will be higher. The further they are, the probability will be lower. And then also, how many standard deviations away is that number? That's kind of what it comes down to. That's what if you ask someone this, okay, well, you have all this data. What's the probability that the average or just some random man in the U.S. is taller than 6'2"? You would say, how many standard deviations are they away from the mean? That's the key. How many? I know that sounds crazy. Standard deviations away. And all this that I'm writing over here, it's more like to give you the idea behind it. And maybe the whole process will make more sense that we outline coming up because we understand why, you know. But you don't really need to know this. This is just kind of giving you an idea, and maybe it'll make more sense. How many standard deviations away from the mean is my data value that I'm interested in? So I guess in this case, it's that 6'2" one. Is that one standard deviation away from the mean? Is it two standard? You know, how far away? Because I know by the empirical rule that 68% of the data values will lie in here within one standard deviation. And then, you know, what do we say? 95% will lie within two standard deviations. So I can probably use the empirical rule to kind of tell based on where is this guy in comparison to the mean? Is he one standard deviation away or two? Yeah, but that's what we're going to calculate. That's what a z-score is. It determines how far in terms of standard deviations a given score is from the mean of the distribution. So you might end up being like 1.7 standard deviations away from the mean. That would mean you're not, like let's say this is 2 standard deviations away from the mean. You're somewhere around here, like this guy maybe. Something like that. And that'll allow us to calculate probability of being that far away, I guess, from the mean. But this is the formula, basically the formula for finding a z-score. And this would have to be, you would have to be given a particular data value like that. Like if someone said, well, find the z-score, I'd say, well, for what? If it was like for the height of a man, okay, for 6'2", or for whatever number of inches that is, I don't know. Then I can calculate a z-score for that. It's that particular value for a piece of data, whatever it is, minus the mean over the standard deviation. So usually you call this guy just x. It's just whatever particular data value you're interested in minus, and then the mean. Usually we're using the sample mean, so I'm going to put x bar over standard deviation. Would we say s? If it's a sample, if it's a sample. Or if you're using population, it would be x minus mu over standard deviation. I think that was the difference. This is if it's a population, but still the same idea. Whatever your data value is minus the mean over divide by the standard deviation, bada bing, bada boom. Now let's try to find the z-score for each of these guys. So a normal distribution, let's say this is just a situation, okay? In some situation, a normal distribution has a mean of 60. God only knows what they're talking about. 60 what? I don't know, don't worry about it. And a standard deviation of 5. So let's see, doesn't say if they're sample or population, so I'm just gonna kind of give them labels, but it could be, and I think maybe I can even just calculate them all right here. I think we have space on the next couple pages, so don't feel like you have to rush this in, but it would just be, okay, your formula, the z-score as was written on the previous slide, is x minus x bar, or I should say mu, that's how I labeled it, over standard deviation. And in this particular case, for all these parts, A, B, C, and D, we're still referring back to this mu and this sigma. Excuse me, it's just the data value or the x that's changing. So mu we said was 60, and then the standard deviation is 15. So all I'm doing is taking this formula and replacing x with each of these one at a time. So I'm just going to write the formula with x missing and then fill it in. It's something minus 60 over 15 for you. We'll see what that is for this guy. Something minus 60 over 15 for this guy. 15, something minus 60 over 15. Okay. And then, you know what, as we go, maybe just to get a feel for this, I hope you don't mind, I'm going to kind of just draw just a rough, very rough sketch of the normal distribution for this, this set of data values that we don't really know about, but we do know the mean is 60. That's what they told us. That's right in the middle. And then the standard deviation is 15. So let's say here, boom, boom. So this from here to here is 15. From here to here is 15 sigma. But in other words, that means that this value is 60 plus 15, so 75. And this value here is 60, take away 15, because we're going to the left, which means it's smaller, so 45. So I should, you know what, I'm kind of just drawing that because I'm expecting, let's say this first one here is 75. Where is he? I'm expecting him to be right here. Anyway, so we'll kind of see how the z-score looks for that. I'm going to replace, just for the first one here, 75 goes in the formula for x. 75 minus 60 is 15, but I'm dividing by 15, so it's 1. So that in that case, my z-score is 1 for 75. And that actually makes sense with the definition of z-score, because if my z-score is right here, 1, z equals 1, that means I'm, just to kind of make sense of it, it means that that data value, 75, is exactly 1 standard deviation away from the mean. But that one, I almost feel like now that I see that answer, I should have been able to guess that, because x is 75. What was our mean? Our mean was 60, and they said our standard deviation is 15. Well, of course, 75 is 15 units away from 60, so I guess I could have known that just by looking at it. But oh well. Let me go try the next one now. 81. I'm going to put that in the formula up here. I'm expecting 81 to be somewhere to the right, probably more a higher z-score because it's going to be further from the mean than the last one was. So probably something larger than 1. So I'll have to do this one. Actually, I have to do some math for 81 subtract 60. Let's see. Why isn't this thing? There we go. 21. Dang it! Why is this thing moving? 21 over 15. Okay, 1.4. 1.4. So it's almost 1.5 standard deviations away from the mean. So if this, I guess this is 1 standard deviation away from the mean, this is 2 standard deviations away from the mean. I'm somewhere around here. This is where my z-score, or this is where my data value of 81 was, somewhere around there. This is, yeah, 2 sigmas, 1 sigma. Okay, just kind of to keep track of what's going on. How about this guy? I've got 60 as my actual data value in part C, but that I'm filling that into the formula. Let's see, 60 minus 60, because I know it's supposed to be the data value minus the mean. In this case, the data value and the mean happen to be the same thing. 60 minus 60 is 0 over 15. But of course, anything divided by, or 0 divided by anything is 0. So that means that, let me think about this, just to make sense of it. The data value is 60 is 0. That's my answer I got for the z-score. Standard deviations away from the mean. Does that make sense? Yeah, it makes sense because the data value is 60. It's right on the mean. The data value I'm given is the mean. So of course it's 0 units away from the mean. It is equal to the mean. That's like if, for the heights of men, if I said, well, I'm 5'8", what's my z-score? Well, I think I said the average man in the US is 5'8". So that would be 0 standard deviations away from the average, because I am average. I'm not taller than average. I'm not shorter than average. I'm just exactly average. So yeah, that's what a z-score of 0 means. That means you're equal to the mean. You're right at the average, which is That's good because clothes will fit easier, right? I'm not gonna have a hard time finding clothes anyway. Okay, how about this last one? 33. Okay, that one I'm expecting to be probably somewhere over here because we said this is a data value of 45. That's one standard deviation away from the mean. So somewhere over here to the left, probably less than one standard deviation from the mean. Anyway, let's see what we get. You got 33 subtract. What am I doing again? Oh, 33 subtract 60 is negative 27. I have to divide that by 15. Let's see. I get, oh, I don't have to put approximately equal to, it's exactly equal to negative 1.8. So I notice that's negative. I think that's the first one we've gotten that's negative. Negative indicates you're to the left of the mean. Indicates, in this case, 1.8. I am 1.8 standard deviations to the left of the mean. So that's the key. When you get a positive z-score, that means your data value is to the right of the mean. If you get a negative z-score, that means your data value is to the left of the mean. So it's good to kind of understand that. Okay, and all this was just space for me to write all that work, but definitely good idea. If you want to, you can write all the work there. Sorry. Okay. Now we're going to get to what we really wanted to do. We want to figure out if I'm given, like I said, a specific data value and someone says, what's the probability of that data value occurring? I want to be able to figure that out. So, okay, and that has to do with percent of data between any two values. So, if, like I said, if you were, I know it's very boring. I keep coming up with the same example, the heights of men, only because I think we've kind of got it in our heads. Maybe that's easier. And I actually remember the average, which is kind of nice. What if I want to know what percent of data is between, well, what percent of men in the US, I know these are people, not data values, are between 5'6" and keeping in mind this is mu, and 6'1" or something, I don't know. And I have to look for the area underneath the curve between 5'6" and 6'1". That's what it'll come down to. What the percent, I want to know what percent of my data is in that shaded area, something like that. This is what we're referring to here. So first thing you would do, which definitely helps, is to draw a diagram of the normal curve indicating the area or percent to be determined, just kind of like we did here. If we happen to be talking about heights of men in the US, use the formula to convert the given values to z-scores. Indicate these z-scores on the diagram. So here, 5'6" and 6'1", I would calculate z-scores. I can't really do that here because I don't remember the standard deviation, but that's what I would do. Calculate z-scores for both of those. You know, for the two, this is the mean. I don't need to calculate his z-score. That's just kind of showing me the middle. Z equals what? I don't know. And then the other, whatever your data values are that you're interested in being between, those are the ones. Find their z values. Yeah, and then indicate these z-scores on the diagram. So now I can go kind of draw another diagram if I want to, where the mean, he's right in the middle. He's a z-score of 0. Like we saw in the example, previous example, if you're equal to the mean, you're a z-score of 0 away from the mean. And then just indicate your z-scores of those two values that you want to be between, whatever they are. Okay. And then what we do is just look up the areas under the curve in a table, which I'll show you pretty soon. And that table, if you need it on the final, it'll be on the final. No need to print it out and bring it, or you don't have to memorize anything. Yeah, like I said here, it will be on the final exam, so don't worry about it. You don't need to memorize it, just know how to use it. Yeah, so that's it. And we'll see an example, it'll make a lot more sense. So but step by step, let's kind of talk about this a little more. To determine the percent of data between any two values, how do you do that? When finding the area to the left of a negative z-score, we use table 12.8. Let me see if I can show you that guy. I'll be right back. Hold on. Okay, sorry, here it is. It even says here at the very top of the table of areas to the left of z when z is negative. So notice, let me see, I'm gonna try to draw on this so you can kind of see the kind of the very leftmost column tells you your z-score. So you're gonna try to find your z-score over here. The next page of this document shows more z-scores, but let's say if your z-score was negative 2.1 or something like that, I'd say, okay, where is that? Oh, here it is, right here. So this is definitely the row I want to look in, because because I've identified my z-score. Yeah, okay, so that's the main idea. Okay, then what about, well, let's see. And then the next page, oops, well, my z-score, when I circled the column, it's kind of circled the wrong one. Here we go. This is like, now that the z-scores, you notice, are getting bigger. I had negative 2.1, now I've got negative 1 point something and negative, the very leftmost column. And then there's another table, as we'll see, let's see. Here, this is the areas to the left of z when z is positive. So just, if you want, if your z-score is negative, you use the first 2 pages of this document, what they call it, table A, and then you'll use table B if your z-score is positive. All right, I better go back to that. Here we go. And then we'll come back and look at that when we need it, that table. But okay, first thing, when finding the area to the left of a negative z-score, we use that table. A negative z-score, notice they said yes, yes, yes. Okay. And then what? As we've kind of discussed. And then when finding the area to the left of a positive z-score, use table 12.8. So notice in that previous slide, the z-score was to the left of the middle. So the area is over on the left side. I'm just stopping right at that z-score. And then if your z-score is positive, that means you're to the right of the mean. So you are on this side of the mean, which means the area under the curve will be bigger because you're still looking at the area to the left of the z-score, but now you're moving to the right. So there's more area to look at. And that's when you'll use table 12.8b. And if you get them mixed up, you say, all right, which one do I use again? 12.8a or 12.8b? Just look for your z-score, whatever it is. If I'm looking for z-score of, I don't know, I'm making this up, 1.3, if I look in table 12.8a, the whole first column is just full of negative z-scores. Negative z-score. So you're going to say, wait, I don't see my z-score in there. My z-score is positive. Oh, I guess I need to look at the other table, 12.8b. So it's not like, yeah, don't worry about trying to remember which one's which or when do I use this one, when do I use that one. You'll know right away you're not looking at the right table because your z-score won't be in there. I can't find a positive z-score in table 12.8a and I can't find a negative one in 12.8b. So yeah, just don't worry about that too much. Okay. To determine the percent of data between any 2 data values, this is where we have to do a little bit of math. And I think this is the part why it's important to draw kind of a picture of what you got going on. Like what was, I think, I can't remember the exact values I said, but I think if we're talking about heights of men, let's say here's the average is 5.8 or 5'8", I should say. But what if I wanted to know what's the probability or what percent of men in the US are between 5'6" and what I say 6'1" or something like that? Can't remember. Probability, or no, I should say, we haven't used the word probability yet, but we'll get there. It's the same thing. What's the percent of men between 5'6", for example, and 6'1"? Well, I'd calculate their z-scores, like they said. I'd look up the values of the z-scores in the table, but then, like it says, I can only find the area to the left of the curve. The table gives me the area to the left of the curve. This right here, what I'm highlighting, that's what the table would give you if you looked up the z-score related to someone that's 5'6". But that's not actually what I want. The percent of men between 5'6" and 6'1" are the men that are here. So I don't really want that yellow part. So what I'll have to do is I'll have to find the area, under the entire curve, like it says. Oh, no. Well, okay, sorry, I messed this up. When finding the area to the right of a z-score, subtract, so, dang it, I shouldn't have said percent of men between, I should say percent of men taller than 6'1". Dang it. So that's I guess the problem, that table only gives you the percent of data values that are to the left. But if you ever want the data values, the percent of data values to the right, you have to take the result away from 1. So if I wanted the percent of men taller than 6'1", it would be 1, which is the entire area under the curve, like they said, minus the area to the left of the z-score for 6'1", whatever that is. I'd find the z-score for 6'1", look it up in the table, that would give me this, the area from here to here, but that's actually not what I want. I want to know the area under the curve to the left, or sorry, to the right. But the table would give me this area. I want this area. Because that's the percentage of men that are taller than 6'1". That's all I have to do is just, yeah. It's not so bad. If you want to know the area beneath the curve on the right, just take the result of the table away from 1. So you have to use a little bit of trickiness, and then to determine the percent of data between any two data values. Sorry, that's what I was getting to with the 5'8" and 6'1". If this is 5'6", here's 6'1", how would you do that? You could use the symmetry of a normal distribution. Okay, yeah, well, don't worry about that. That's not helpful. There we go. This is more like it. This is what I was trying to allude to. Sorry, when I had the 5'6" and the 6'1". If this is my person that's 5'6" and here's 6'1" over here, and I want to know what's the probability of me being between here and here, I have to kind of use some I don't know, use some logic to figure it out, because I know that once I calculate the z-score for you is whatever, z-score for you is whatever. I look them up in the table. I should color code them. Let's say this is the green, the person that's 6 foot, or dang it, person that's 5'6", their z-score, let's say he's green. That's a green z-score. I look it up, that would give me the area to the left. The table always gives you the area to the left of the curve. That's not actually what I want, but it will give me what I want eventually. And then let's say that if I find the z-score for a man that's 6'1", and I look it up in the table, it'll give me the area beneath the curve to the left of it. So really, when I'm looking at that curve that I drew, what I want is the orange area. The yellow area is too big. The green area is the wrong area. The orange area, sorry if you're colorblind, but that's between here and here. It's the highlighted area or yellow area. Take away the green area. So that's what I have to do, is I'll just have to calculate z-scores and subtract the values I get from the table, kind of like they show here. Use the z-score for the rightmost data value to find the value in the table, and then the same thing with the left one, and then we'll subtract them, and that'll give me the area between. That's the idea. Then change the areas you found in step 3 to percents as explained earlier. Yeah, if you found the value to be 0.89 in the table, that means that's 89%. That's all. Yeah, no big deal. So that's all they mean for that one. Okay, maybe we'll actually think about this. Let's see. Let's do an example here. Assume the lengths of time for a horseback ride on the trail at Triple R Ranch is normally distributed with all that I don't really give a crap about, except now I see the mean is 3.2 hours and the standard deviation is 0.4 hours. What percent of horseback rides last at least 3.2 hours? Oh, why am I drawing that? Don't need to draw the vertical curve. I think I'm so used to algebra, or there's a y-axis also. We're not really thinking about that yet. Here, boom. Here's a normal curve. It says the mean right there is 3.2 areas, and then standard deviation is 0.4. It sounds like they're asking about what percent of horseback rides last at least 3.2 hours. What does that mean? At least, that means 3.2 hours or more. Where are the values on the x-axis, for example, that are more? They're to the right of 3.2. So from here on, this is what the area I want. So I'm gonna have to, first thing, like they said, I need to calculate the z-score for that. First, calculate z-score for this data value that they gave me in part A. I mean, there'll be another part B where they probably talk about a different data value, but it sounds like the average is right in the middle, and that's what I'm interested in. What percent of horseback rides last at least 3.2 hours? So that I think I can probably guess the answer, but it's good to go through the process, even if I think we can kind of use logic to figure out the answer here. But okay, remember the z-score formula is your data value minus the mean over the standard deviation. So our data value is 3.2 minus, and then the mean was given to us in the problem. Here we go, 3.2, and I shouldn't be surprised. Doesn't even matter what the standard deviation is, it's 0 over 0.4. So 0. So I can look up in the table. It's either 12.8 A or B, because 0 I think is right in the middle. He's not a negative z-score, he's not a positive z-score. Look him up in the table. Okay, let's see. See if I can find that guy. Hold on.